39 Arthur Sweeny lecture, and I have to make a confession. I feel like in my first day of teaching. I all the time organize these things for 9 years, but it's the first time when I have to talk in the quality of chair. So my name is Andrei Gitianu. I am the chair of chemistry for you which you don't know me. And I welcome you in our house. So I want to know if it's any Professor Sweeny students here? Anybody? One there. Thank you for coming. And I know Janet Brown is still basically, it's trying to walk the stairs. It's a first student, research student of Professor Sweeny. So she was in the art gallery. So Professor Sweeny here began his career a hunter in 1930 and served this college for 44 years. And he was one of the pioneers in cancer research. And some of his students are still around, being physicians or professor or doing things which are important for community. And most of the time, basically, they are coming back. How this Sweeny lecture come together? It's through his students. He was so beloved when he retired in '74. His former students went to the president at that time and basically asked for a lecture for him. And that lecture grew. It's what is today. And basically, more memory about Professor Sweeny will be given by the Professor Lazarus, which I invite him to talk a little bit.
Very good.
And I'll come back. Don't worry.
This is a picture actually taken at the Sweeny lecture in the little room where we had earlier today, we had a reception. Well, actually, we had lunch. Originally, we used to use it for the reception before the Sweeny lecture, and this picture was taken. The person on the left, for those who don't know him, is Professor Ruben Baumgarten, who was our chair for 17 and a half years. In the middle, you all recognize Professor Sweeny by now. And on the right is some guy I don't know. I don't know where he came from. Did they let him in that day? I mean, how did he get in there? And then the other thing about him, you sure it wasn't photoshopped, right?
Yeah,
no? Okay. That's the latest thing, you know. Okay. So anyway, I've been to, I believe, every Sweeny lecture, starting with the first one. And I remember how it got started before the first one, because a student, one of Professor Sweeny's students, who was a very successful chemist, had sent a letter to President Leonard Leaf. Well, we're getting a little explosion there. To President Leonard Leaf, asking him, saying that because of Professor Sweeny's great influence on his students, he felt it would be appropriate to start a lecture in honor of Professor Sweeny. And at the beginning, it wasn't a memorial lecture because Professor Sweeny came for all the years he was able to, and then later on in his life, he had to move into an assisted living facility. He couldn't really come anymore, and sometimes members of his family came too. So it was really very nice right from the beginning. Professor Sweeny, as Professor Giuliano mentioned, started his career at Hunter College around 1930, so he was. This was then Hunter College in the Bronx. In 1968, when Lehman College separated from Hunter College, Professor Sweeny chose to come here instead of staying at Hunter College in Manhattan. Professor Sweeny was well loved by all his students. He took, I remember one of his students who had spoken here said he used to bring students up to his house in Pleasantville and go fishing with them. And he was also a person who inspired many students. And there were cases of even students who were going to give up on the thing that they wanted to do. Professor Sweeny could sit down, he just knew how to talk to people, and he'd give them encouragement and tell them they can do what they thought they couldn't do. And it resulted in many success stories because he was that kind of person. He was a person of great character, which is one of the things I admired most about him. The first time I met him, he had come down to Lehman for a visit shortly after I had been appointed to the faculty here, and I got to sit and talk with him. And I was impressed by both his character and his intellect, which, even though he was no youngster, was very much intact. And I enjoyed that conversation enormously. Professor Sweeney's students, as was mentioned before, marked what a terrific inspiration he was, not only by starting this lecture, by getting President Leaf to start the lecture, but by showing up regularly. We always have some of Professor Sweeney's students here. I just think he was inspiring and fine and really wonderful person. And it became a memorial lecture after he passed away. He was, if I recall, about 94 years old. In any event, I just wanted to let everyone know the kind of person for whom this lecture was named. Take care. Have a good day. You don't want me to leave yet?
A few months ago, asking Professor Lazarus to speak about Professor Sweeny, Professor Lazarus said, if I'm not wrong, I'm Professor Sweeny replacement. So here is Professor Sweeny replacement. He forgot to mention that.
Right. I came here in 1974. Professor Sweeny had retired in 74. I'm fairly sure the department got a line when he retired, and I ended up being the one hired on that line. So I have
a long and nice career at Lehman. How many years? 45 years?
It'll be on September 1st, 45 years.
So more than Professor Sweeny?
A little bit.
A little bit, okay. Thank you for service.
Thank you.
So, moving further a little bit, I want to point out the presence of Janet Brown, the first research student of Professor Sweeny, here in the second row. Yes? So we have two students of Professor Sweeny. Yes? Thank you for coming, and thank you for keeping the memory alive. And also I want to point the presence of our newest provost, Peter Osu, here in the first row. Yes? And of course of the Dean Mills, which is here. She should be here. Okay, yes. She is. Okay. Let's go a little bit farther. What do you think about these names? University of Michigan at Ann Arbor, Berkeley, University of Florida, Arizona State. What do you think? It's a good names? Good names, yes. Are you proud that Lehman College is among that? Yeah? So, what is this? That is basically where we are, among these names. And how this is coming? Basically, Lehman College was named among one of the 20 best pre-med schools in the country with hybrid elements in their programs. And that happened this year in 2019. And we are very proud of this achievement. And remember, we start from here, big names. We are among the big names, which are driving further. So, how is this coming to the chemistry? If you are Googling, yes, and I provide you with a link in my letter to you, yes. If you are Googling, you will see that we are number 16, which is a good place. But how it's coming that chemistry is so important is basically we develop a BA for pre-med, which basically have elements of learning online or flipped classroom. And I want to mention here a few names. Professor Mills, please. She helped to develop all of this. Yes. Donna McGregor, who is not here, unfortunately. And the third name is Kelvin Scott, our pre-med advisor. Without him, nothing will happen. So I encourage you to read online, and basically to read that everything is about chemistry. Yeah. So now it's about achievement, yes? It's a meeting where we are meet to say what we are doing. And we have faculty achievement and student achievement. Let's start with the faculty. Professor Kurtzman got his first R01 grant. It's basically first R01 grant in chemistry and the second in the college. That is a very big thing, that it's a recognition that he's doing top-notch research. The second thing is basically Dr. Melissa Derry, our newest hire. She got a SCORE NIH grant, SCORE 2 grant. She was highlighted among 30 promising early career professionals by Society of Nuclear Medicine and Molecular Imaging. And also in this summer, she will be visiting professor of Brookhaven National Institute, and she will go with 2 students. Am I right, Melissa? Congratulations, all of you. And of course, our achievements are connected with our students, yes? So, Professor Gustavo Lopez here, and Professor McGregor got a grant, a RISE grant, which is called Lehman on the Rise. And they are training the next generation of the PhD students, format Lehman, which will go to in PhD programs, yes? They are pre-trained to resist and to develop in the PhD program. But nothing compare for us. We are here for a reason. We are here for a reason of being a professor, to enjoy the success of our students. Yes, that is the most important achievement. So the achievements of the students are basically this. We have 21, again, potential alumni, basically 21 kids registered for graduation. Yes, it's about you guys, yes? In this moment, in the department, we have 12 doctoral students, and it's possible another 2 or 3 to join from September. We have 14 undergraduate outwards in the past year. So basically, they were published in peer-reviewed papers, which is pretty big. Yes, so they were active in the lab doing research. One graduate student, one undergraduate is going to the graduate student headers. Yeah. And we have, it's early in the process, I have only 3 names now. 3 kids going, 3 of our students going to the research undergraduate experience over the summer. These are transformational, are not trivial, it's very important. It's Jennifer Guzman, is going to Columbia. Vladislav Bondar is going to Brookhaven with Melissa Derry, Dr. Derry. And Siobhan Wright, also working with Dr. Derry, is going to NIH. So these are the names which I have right now. Okay, so that are the achievements for this year. This is my report to you, to the alumni, to the friends, to everybody. So let's go now to the purpose of the day. Basically, our speaker today, it's Professor Joseph Francisco, yes? Joe, it's coming, it's for you. So my role is finishing soon. So he graduated from University of Texas, Austin, and then she got his PhD in chemical physics. God, a lot of Schrödinger, I think, yes? Yes, from MIT. So he received a lot of awards and distinguished, but I want to mention one of that. He receives a Percy L. Julian Award for pure and applied research. And he's a fellow of many societies. American Chemical Society, Physical Society, Association for Advance in Science. Basically, he got a lot of distinction from different governments, like German government, Italy. He was working with as an invited professor in France. And he was the president of the National Organization for Professional Advancement of Black Chemists and Chemical Engineers between 2005 and 2007. He currently serves on the Alexander von Humboldt Foundation International Advisory Board, and also in Board of Trustees of Gordon Research Conferences. And President Obama appointed Dr. Francisco as a member of the President's Committee on the National Medal of Science, serving between 2010 and 2015. He also is a Dr. Honoris Causa of 5 universities, if I'm not wrong. So, pretty accomplished. For this reason, I invite him to give us a talk to deliver today the 39th Sweeny lecture. Professor Francisco? Hey.
Are we, yeah?
Yes.
Okay,
Yeah,
we're ready.
yes.
Andre, thank you. Come
Yeah.
here. Come here. Beautiful introduction. Thank you, everybody. Can you all hear me? Yes. Okay, good. Well, I'm just been delighted to really be here, and I really want to thank the organizing committee for thinking about me to come to Lehman College. It's a great discovery, not only just the college, but I discovered the Bronx, you know, as well. And so, but also just the wonderful students and what you're doing and where you're going and learning about your dreams and your ambition and the faculty who are helping you to realize that. It's just been a very, very special day. And unfortunately, you know, the day has been too quick, you know, for me. It's gone by so quickly, and I feel I have so much more to learn about this special community. But now it's my time to tell you a little bit about some of the work that we do and what excites me every day and why I'm excited to get up every morning to go to work and do what I do. As the title says, I'm going to be talking about complexes, from complexes to aerosol, new site in atmospheric chemistry. Most excellent. Thank you, my friend. You know, in the atmosphere, we look up in the sky, and well, you didn't really want to look up there yesterday or this morning, but if you look up there now, it's beautiful sunny weather, a few little clouds. It's just beautiful. And little do we realize that there's just a lot of chemistry going on up there, just a lot. And in fact, there are hundreds of reactions taking place, you know, like on a clear day or even on a cloudy day. There's chemistry still going on. And if I look at all the chemistry and try to kind of compartmentalize that chemistry, I can kind of compartmentalize that chemistry into kind of 3 boxes. And those first box I kind of like to refer to as chemistry that are first order processes. So in the atmosphere, you know, we don't have a big Bunsen burner up there, although some of us like to think the sun as a big Bunsen burner. But that sun initiates chemistry because molecules that are floating around in the atmosphere are absorbing photons, and those photons represent energy, and that energy actually initiates bond-breaking processes and in a first order way. So how chemistry in the atmosphere is initiated is through photochemistry, and we call that a first order process. And this is an example of one of the typical major first order processes, how ozone absorbs radiation from the solar spectrum coming in from the sun. And then it initiates a photodissociation. There's a second category of reactions, and that second category of reactions we call two-body reactions. So species that are produced from that photodissociation, when they come into contact with another chemical entity floating around in the air, it will react. And so you kind of think of A plus B coming together, and it produces a reaction, produces new products. And the question is, what are those products? And what is the chemistry? And what are health consequences of the evolution of that chemistry? And so when I look at the thousands of the reactions that are taking place in the atmosphere, the majority of those reactions are categorized in this two-body processes. Photodissociation is a small number of reactions that are initiated by photodissociation. But even though it's a small number, it's very important chemistry that propagates chemistry throughout the atmosphere. Now, when I was looking at the invitation to come and deliver this Sweeny lecture, I noticed in years past you've had nothing but Nobel laureates. And I said, oh dear, okay. Now, here's what I'm going to say about Nobel laureates in my lecture here. Well, there are a couple of that really discovered photodissociation processes and really responsible for that. And in fact, Rudy Marcus, who's still alive and is currently at Caltech, actually was one of the pioneers who laid out the framework in fundamental physics and chemistry of how molecules absorb, energy and photodissociate. And so he got the Nobel Prize, for that fundamental contribution, as well as contributions in electron energy transfer processes. That was what he's most noted for, but the groundbreaking foundational work was then looking at unimolecular dissociation processes, and that involves photodissociation reactions as a subset. The second group of Nobel Prizes given for really fundamentally understanding the hows and why, when two molecules come together, they react, and doing the fundamental laying out, that fundamental foundation was given, I think it's in 1986 with Dudley Hirschbach at Harvard, John Polanyi at University of Toronto, and Yuan Li at University of California, Berkeley. And they laid out a lot of the foundation about the hows and whys these reactions take place based on their structure and chemical makeup. Now there's a third body of reactions that take place in the atmosphere. This turns out to be a small number of reactions that follow this schema, and this schema of what we call three-body reactions. In this example of three-body reactions, they're small body, but they're very, very important. So when the sun goes down and there's no more energy to initiate a lot of these reactions, and the reactions take place, the sun goes down, what shuts off a lot of chemistry at nighttime are these three-body reactions, where the reactive species now come together. Oops. Well, here we go. I'll figure this out. Oh, nope, I'm going in the wrong direction. Okay, all right, so no problem. Well, that is a problem. We're getting back. Here we go. And one more. So what happens in terms of these systems, and I kind of like to describe this, that you got oxygen atom. This is a case where from the photodissociation of ozone, that oxygen atom can combine with O2 to give ozone, but when it's produced, it has a lot of energy in it, and so that molecule can go back and give you these original reactants. But what kind of stabilizes it is when it comes into contact with a third partner, and that third partner acts to remove energy from that hot ozone, and that kind of stabilizes. That's kind of how it happens. Now I'll let you know that a number of researchers have been working on the hows and whys these reactions take place. One of the pioneers and major contributors to looking at the hows and whys three-body reactions take place is Jürgen Troer in Göttingen, Universität Göttingen in Germany. And he's actually done a lot of work pioneering this energy transfer model, where you now have oxygen atom combining with O2 to give this ozone, which is very vibrationally hot, but you rely upon a third body to remove that energy and hence stabilize that. We call that the energy transfer model or energy transfer mechanism. Now, there's a second mechanism that can really describe that same outcome, and the outcome that you get is A plus B given AB, and it's called the chaperone mechanism. And I like to describe, I'm a father of 3 daughters, so this is my daughter, and this is me, and this is some boy who came around wanted to find out about homework. Okay, and we call this the chaperone mechanism for good reason. Okay, now I'm gonna talk a little bit about this because that chaperone mechanism is special, for obvious reasons. But this now. I see, someone here, I just turned to the slide and I go, oh my God, there's chemistry and a lot of it. So don't get scared by all these chemical reactions. There's not going to be a pop quiz, or you don't have to memorize any of that. But I put this up to kind of give you a little example of what goes into an atmospheric chemistry model. This is the kind of chemistry that goes into an atmospheric chemistry model. We run that on out. We look at what's the kinds of species that are produced. We find out how much is produced. And then we kind of rely upon in situ measurements from aircrafts or balloons, are these kinds of platforms to go, our LIDAR as an example, to go out and make measurements of chemical entities up there. And if we know the chemistry very well, and we propagate that chemistry through these models, we should be able to get some confirmation in terms of what these various measurement platforms are actually seeing up in the atmosphere. And this is how the chemistry evolves, and these are kinds of the rates that tells you how fast these things take place. Now, one thing I do want you to stare at and take a look at and kind of remember is look for water. Look for water in there. Take a little time and look for water. Where is it? Now, I'm going to tell you where it is, but just think of this as a simple model, and I just told you that there are just hundreds of reactions. Where is the water? And of course, we know about water from yesterday and a little bit this morning. There's a lot of it in the atmosphere. Where is the water represented in the chemistry? I want to leave you that question. We're going to come back to that question momentarily. But let's move forward. And now, one thing I could do is go through and talk about each one of those reactions in that model and the chemistry associated. I really will not do that, okay? But what I'm going to do is pick on just a couple of very important chemical entities. And the 2 chemical entities I'm going to be picking on a little bit today is OH radical and HO2. OH radical is our little atmospheric detergent. OH radical cleans up a lot of the stuff that we throw up into the atmosphere. How many of you have ever played Pac-Man and Pac-Lady, Pac-Girl? Okay, I know there are more hands than that. Okay, I know there are more hands than that. But, you know, OH goes off, and whatever comes out of a smokestack or won't come out of a tailpipe, or what happens, you know, when you're cooking and you just go up and just get enthralled by, you know, what's on television, and the smoke alarm goes out, and you open up your window to blow all that smoke on out. OH just goes after that stuff and just breaks it down and cleans it up. So it turns out to be our major atmospheric detergent. All right, and of course, when it breaks things down, ozone also has another, OH has another important benefit, and that anything that results from incomplete combustion and hence emits CO, carbon monoxide in the atmosphere, which is not good, that we don't want to breathe. OH actually turns that CO into CO2. And that's a good thing. Otherwise, we'd be kind of choking on our own pollution, and OH prevents and minimizes that from happening. And of course, then in the process, it gives HO2, and that HO2 ultimately comes back and keeps in the nice balance of helping to regenerate OH so it can go off and do its this atmospheric cleansing. Now, I want to kind of pick on this reaction, and I want you to kind of remember that, and I'm going to pick on OH and HO2. And one of the reasons why I'm going to pick on that is the following. You know, one of the questions that people we've kind of been thinking about with all our man-made activity, and all the stuff that we're throwing up there, and with the increased number of vehicles, and granted we've done a good job with catalytic converters and stuff, and there's still some emissions that go up into the atmosphere from various sources. The question is, with all that activity, are we compromising the oxidative capacity of our atmosphere? What do I mean by oxidative capacity of our atmosphere? What is the ability of our atmosphere to remove pollutants such that when you go to sleep at night and you wake up in the morning, go out to work, you have clean air to breathe? Are we reaching a point where we're compromising that or slowing that down? How would we know when we've reached that point? So actually, that was a really interesting and profound question that researchers around the globe really started to raise, and really began to kind of answer that question. Again, two of the key species, the key to addressing that question is how much OH we have and how much HO2 we have. And that triggered a lot of worldwide engagement and efforts to measure how much OH is up there and how much HO2 is up there. And of course, if you understand that balance, then now you can get a sense and a gauge, to what extent our, human activity is compromising our ability of our atmosphere to oxidize and get rid of various pollutants. So we've collaborated with a group in Japan, and this kind of highlights some of the studies that they were doing. Although there were groups all over the world who were trying to get a handle how much OH, get a handle how much HO2, or get a handle on how much OH plus HO2 we had. And in fact, the answer to that question will hopefully, allow us to look at and assess the oxidative capacity of our atmosphere for the first time. Really? Really? Well, let's talk about it, okay? So, when the field measurements, people did the measurements, and they came back and worked with their the modeling, atmospheric modeling guys, and ran off the models. If we have all the right chemistry, then all the measurements and then all the modeling should all be on the same line if they're in total agreement. But you can see that there's not. And in fact, what we find is that the models really overestimate the HO2, and so what we realized that there was missing chemistry and missing lost sources of chemistry that the models were not really accounting for. Or what is that chemistry? So a lot of people, again, being very, very smart, a lot of smart colleagues from around the globe kind of look at this of being, from a very, perspective. Well, given all the kinds of chemistry in those models, how do we know all that chemistry and the measurements of their rates are correct in the first place? Let's go and try to validate some of that chemistry. And that's what some of my colleagues at Jet Propulsion Laboratory started to do. And they kind of reckoned where maybe there was some uncertainty in all the measurements that went into the model was in the HO2 plus HO2 self-reaction involving a third body. So now this is that three-body reaction part that I introduced is now coming in to tie in. And so they went out and really did some beautiful measurements, very accurate measurements, measuring the reactivity of that reaction and how fast that reaction was. And they got some good rate constants that they can actually use fundamental rate theory of Jürgen-Truhr to match and explain, and that was great. Under conditions, some of the conditions that really matched the atmosphere where the third body was argon or helium or whatever. But something happened when they decided, let's look at this reaction in the presence of water. And one of the things they started to see is some things that were really counterintuitive. And some of the things they started to see that was counterintuitive for that reaction in the presence of water is that it had a profound dependence on water pressure. In fact, the reaction was accelerating as you were adding water. But even more profound and counterintuitive was as they lowered the temperature, the reaction was accelerating. And that defies everything about chemistry that any one of you have taken a chemistry course know. That when you want to accelerate a reaction, you turn up the heat. If you want to slow down a reaction, you turn down the temperature. And turn downing the temperature here was accelerating. So this was really counterintuitive. And it actually suggested that the chemistry, underlying chemistry, was far more complicated than in this sort of simple notation of a three-body reaction process. And in fact, what my colleagues at Jet Propulsion Laboratory had actually proposed is that this HO2, when it saw water, it formed a complex, and now that complex reacted with another HO2 to give the products that they saw. And if you put this chemistry in the model and model that, you can explain everything. But we also know that you can never really prove a chemical mechanism. You can only disprove. And so there was really nothing, real evidence to show that this was truly the underlying chemistry, but the measurements supported its suggestion. So we were actually brought in by my colleagues at Jet Propulsion Laboratory in Caltech to kind of understand if an HO2 water complex existed. And our goal was to try to get out there and kind of disprove this, that such an entity did not exist. We were not able to disprove that entity didn't exist. In fact, all the data was suggesting that this entity was strongly stable and unusually stable than what we would think. And what's unusual about it is that this HO2 water complex formed two hydrogen bonds, one a very strong hydrogen bond, one a very normal hydrogen bond, and it actually had a binding energy of around 6 kcals, which is stronger than the hydrogen bond energy in water dimer, which we all know is what we've used and learned to understand hydrogen bonding for all kind of biological systems and processes. So we're actually seeing hydrogen bonding interactions with these atmospheric radicals in water that are unusually strong. And in fact, some of the hydrogen bonding interactions that we saw with some of these radicals, the binding energy reached as high as 20 kcals. Whereas your typical hydrogen bond from water dimer is about 4.9 kcals, 20. And so what that said, if any atmospheric radical species saw water as it's moving around in space in our atmosphere and it collides, it's going to stick. Okay, it's going to stick like fly on fly paper. Okay. So we went out with that suggestion based upon the calculations, and in 2006 there was a group in Japan of Professor Endo, who actually did some Fourier transform microwave spectroscopy, producing the HO2 water complex in the molecular beam in a jet, and they backed out the structure. And you can see this very strong and this very, standard hydrogen bond in a double hydrogen bonded complex scenario. And that we were excited. And of course, we were excited about that, but at the same time, we were motivated by that to see in the laboratory at Caltech if we can actually see this HO2 water complex under atmospheric conditions. And this describes some of the experimental stuff. This was data that was taken in Sweden by Bernd Nylander. And this is calculations we had done about the HO2 water complex. Independent of his work, we only found out about each other's work when the papers were under review, and found that our calculations replicated many of his experimental observables within about 3%, and we were excited and encouraged by that. These are the experiments that my graduate student Simone did at JPL, where he actually produced HO2 in this sort of flow discharge arrangement, and the HO2 flowed in this white cell, where he came in with an infrared beam, high resolution infrared beam, detected the HO2. Once HO2 came out of the stream and encountered water. And this is the spectra that he saw, and you kind of look at that and say, geez, that's noise. That's not spectra, that's real. And those are lines, and he was able to identify roughly about 92% of the lines in this spectra. But what you also see is that once you add water in here, you see new spectral features grow in which he was able to assign to the HO2 water complex. Now we're getting to something interesting here. That spectroscopy, good stuff, okay? But here's now the interesting stuff. So now if you know how to probe for HO2, you now know how to probe for your water. You know how much water you have. You know how much HO2 you have. And of course now as you add water, you can measure your loss, and this gives you kind of loss on the assumption that the loss is going entirely to HO2 water complex. You can back out an equilibrium constant, and then you can plot that equilibrium constant, the log of that with time, and get a Van Hoff plot. This is the points here are the experimental points and extrapolated points from the experimental data. This purple line that runs through the data are strictly from ab initio data, totally unfitted, totally, unaltered. And so what it shows is that we can actually get pretty well within the experiment, with the ab initio calculations, and that's great. But here's the importance of that work as a totality. So now we know how much HO2 water complexes would be at any point in the atmosphere. All we need to know is how much HO2 we have, how much water we have. With the equilibrium constant and the temperature, we can back out how much HO2 water we have. And with that, what we found was down in the lower region of the atmosphere, actually below 10 kilometers, roughly 30% of the HO2 was tied up as HO2 water complex. So now I'm going to ask a dumb question. And here's my dumb question. If I'm trying to get a handle on the oxidative capacity of the atmosphere, and I'm going to measure OH and I'm going to measure HO2, by just doing those two measurements alone and knowing that HO2 water accounts for about 30%, with those two measurements alone, do I have a good measure of the oxidative capacity of the atmosphere? No. Because you're missing 30% of the budget. You're missing 30% of the budget. Okay? You're missing 30% of the budget. And that was actually profound, and that was a paradigm shift. That was a paradigm shift because now what it started to say, in regions of the atmosphere where there are high water vapor profiles, there are complexes that are there. And a lot of those complexes, if you're using an instrument that targets the original, you're going to be missing out a significant source of that original that's tied up in a complex. So you not only have to understand your original radical, but you have to understand how it interacts with water and also get a measurement and accountability of that. This is some actually modeling work that's done by 3D global modeling work that's done by a colleague of mine along with one of my former graduate students who's also on the faculty at BYU. And they were looking at other RO2, not just HO2, and you can kind of see that these complexes are all over the globe, and particularly in the tropical regions where the water vapor profiles are, quite high. So now I'm going to ask, the question, if you're now going to be producing these radical species, and they're going to be up there, they're going to be surviving up there, what are they going to be doing? What chemical role are they going to be playing, if at all? And how do we know what that chemical role happens to be? And that was something that we really started to address. And I call this water-facilitated chemistry. Now I'm going to pick on this right now from a standpoint of the following. A consequence of climate change right now is heating up the oceans. And heating up those oceans means that there's being an injection of water into the atmosphere. In fact, now you have that water being ejected up into the atmosphere. What is the consequence beyond just heavy rains, that we see? But what is the consequence of that additional water, on chemistry in the atmosphere? That's becoming a very important question to kind of, answer. And that was one of the questions that we have really started to look and address in our work in our laboratory. Now I'm going to pick on this reaction OH plus HCl. And I want to pick on it because it looks simple. Looks very, very simple. And, and it looks simple because what you expect as the outcome is that OH is going to extract off that hydrogen from HCl. You're going to get water plus chlorine. Now, it's simple, but that has some potential consequences. And one of the consequences of which is that reaction is regenerating chlorine atoms. And chlorine atoms is responsible for depletion of ozone. When the chlorine is tied up in the form of HCl, it makes that chlorine inactive, and we rely upon the atmosphere to rain that stuff on out, or clouds to absorb it and rain it on out. And that's how the atmosphere cleanses itself of a lot of that kind of deleterious chemistry. And so what we know about that HCl as being a strong source of tying up that chlorine is that, well, you don't have the right kind of photons to bring that chemistry back in. You need very, very short wavelengths, which can only happen very high up in the atmosphere, and HCl doesn't make it there. So photochemistry HCl is not going to be important. Again, you know, if OH reacts with HCl and generates this chlorine, from the measurements on that reaction just by itself, it's very slow, on the order of 10 to the minus 13. That's kind of slow. And so people have kind of ruled that out most of the time as having really an insignificant role in re-injecting chlorine. And actually, not only just the experiments have been done to make those measurements and accurate measurements, but there are calculations mapping out the potential energy surface. And if we have an accurate potential energy surface of that reaction, we should be able to reproduce those rates, in which we do. And this is kind of a mapping of that potential energy surface, where the OH forms a kind of pre-reactive complex. It extracts off the hydrogen, but it goes through a barrier and then produces the products. And you can see it's roughly about a 2 kilocalorie barrier, which slows it down just enough to make it really insignificant. Very simple. Now, what happens if we add one water molecule to this reaction? What happens? Well, that water starts interacting with the OH. The water interacts with the HCl. It forms a lot of these complexes. And now I'm just going to go back here. This one little singular step in terms of, this one little singular step in terms of going through this pathway to produce products. When you add water, you now have introduced many more pathways. But one of the things that we discovered is by adding that water acts as a catalyst. And so now it actually catalyzes new pathways to get to these products in the most energy and cost-effective way. And in fact, one of the things that we found is that there are two kinetic kind of regimes where in the absence of water, that reaction is slow. But in the presence of water, we can accelerate that reaction anywhere from a factor of 4 to a factor of 10. So now one of the things it starts to say, as we're injecting more water into the atmosphere, we need to now start to think about what are the consequences that water on reactions. Is it going to accelerate those reactions? Is it going to slow those reactions down? Are we going to see the same kind of products? These are things that we've been doing in our laboratory and finding interesting results that you can even change the product distributions of the kinds of products that you actually see by the introduction of one water molecule into reaction. Now think about, remember that long slide of all those reactions I put up there? You remember that? Think about one water interaction with all those reactions, what the magnitude and impact of that chemistry happens to be. And you need you to kind of think through that. Well, nevertheless, this kind of describes a little bit of the summary of that. But now, one of the things I want to kind of talk about, and this started to kind of be a little bit profound for me, and that is, everything I've talked about right now is chemistry that happens in the vapor phase, with water in the vapor phase. Like you noticed last night and early this morning, you got clouds and you got water droplets. And what about chemistry on the cloud and water droplets? Now, initially, one of the things in the roles that we viewed clouds were simply as a scatter of radiation. Unwanted radiation got scattered back out in space. And it kind of made sure we kept the balance, a radiation balance of, of radiation hitting the surface. But this water and radical interaction with water says that clouds may have a more influential role in chemistry than we have ever really thought through before. And the chemical role of clouds had really been pretty much ignored. Now, some of my colleagues would say, well, Joe, that's not true. Okay, all right, so maybe I'm overhyping. And where I may be overhyping is the following, is that, yes, there's been a lot of chemistry looking at chemistry within the bulk of the clouds, solution chemistry, okay? But you got to get something from the air into the bulk of the cloud where chemistry can take place. And I'm not clear that everything that from the air that hits the cloud droplet surface will go into the bulk. And that question had never really been addressed. Now that question was asked, and and some colleagues kind of tackled that question from this perspective and say, well, okay, we got something that comes from the gas phase. It's going to see this droplet, and two things can happen. It can just bounce back on off in space, or once it hits this droplet, it can go on into the bulk, and you got solution chemistry that takes over, and we can tell you what happens there. But I ask, what happens here? What happens there? Is this a true representation of what happens at that interface? So I was really kind of curious about that. So this is where an interesting moment for me happened. And so when I was president of the American Chemical Society, I was away a lot. And the students enjoyed that moment, you know, and I just kind of, but when I returned, they were always there in the lab, and, you know, oh, okay, all right, show me some results, yeah, okay, it's great, and then I'm off again on ACS business. Until I got a call from the provost, said, Joe, when are you coming back to Purdue University? Now, why would a provost want to call me? He said, well, I want to talk to you about your students. They're using up all the computer time from Purdue University, and we're getting complaints from the Dean of Engineering. And I really want to find out what your students are doing. And of course, I went shaking. Oh, the provost. You know what I mean. You know what I mean. But what the students did, and if I was at Purdue and they had talked to me about this idea, I probably would have shut it down. Because what they said was the following. Well, Professor Francisco, what we're going to do is we're going to take HO2 molecules somewhere up over here, and we're going to take a line from its center of mass to the center of mass of this 20 water molecule structure that represented 4 monolayers of a water droplet. So they took a little slice of a water droplet, and now they're going to optimize everything, you know, on the computer. And at that time, that's a big calculation, you know. And they figured out how to just circumvent all computer resources over to their job. You know, students are very bright. And of course, I would have raised those questions. No, you can't do that. The engineering dean is not going to be happy. He's going to talk to my boss, and the science dean is not going to be happy. No, don't do that, okay? Well, see, they didn't have that, okay? And they went off and did it. All right, and so when I got back, I wanted to kind of learn what do they do and how to, et cetera. And this is what they showed me. And this was really profound. And this was a game changer. And I'm glad I wasn't there. I really was glad I wasn't there, because it really was a game changer. And it's going to be, you will see how game changed everything in the conversation, you know, for the chemistry, and even define new chemistry. And I'm going to show you that. But I want you to remember this, because I really now need to give a lot of creative thanks to my students for really taking that creative moment to do things when I wasn't there. A little nerve-wracking, but I thank them for it. But actually what they found is they brought that HO2 up to that water surface. That HO2 fell into a well. But they were under the traditional thinking that the HO2 was going to go into the bulk, where that bulk chemistry was going to take place. But in order to get the HO2 into that bulk, there had to be a lot of water rearrangements in order to accommodate the HO2 into the bulk. And that's what you're kind of seeing there. And that made good sense. But I was curious about what did this look like? You know, what was it doing at this point? There's clearly a well there. What it was doing? And then when I asked them to go and show me that, this is what they came back with. And this was the game changer, and kind of set the paradigm for some years to go, and years to go now, even more. We found that the HO2 didn't want to go into the bulk. It was really happy at the top of that interface. And instead of complexing with one water, it was happy to complex with two waters. With two, again, you know, hydrogen bonds with the double hydrogen bond, and it was stable there, and it was happy there. And this is a little bit kind of how it looks like when we did molecular dynamics simulations on that. So there's a colleague of mine at Kyoto University in Japan who I went over and talked to. I got an invitation to go over there and talk to about this work. And he kind of introduced me to molecular dynamics. And one of the things he wanted to kind of do is try HO2. We were doing an ab initio, and that's at 0 Kelvin, and anything will stick and stay at 0 Kelvin, okay? And he wanted to kind of model this in a more realistic scenario, and he felt he can do that with molecular dynamics, giving these molecules some velocity, and seeing which, given velocity, if they would actually really stick. And this is kind of the modeling scenario that he set up to run. And actually what we found was that regardless of the trajectories, regardless of the velocities that you use of the HO2, that when the HO2 saw that surface, it stuck. And there were few events where the HO2 bounced off and reflected. Well, why was that profound? Well, that's profound because now it puts everything we calculated in consistency. Given the strong binding energy of water with the HO2, says it's going to stick, and the molecular dynamics says it's going to stick. But it became inconsistent with the experimental observations that showed that when they did HO2 and produced a gas of HO2 and they dropped the water droplet through that gas, what these calculations says is that every time an HO2 encountered that water droplet surface, the HO2 was going to stick. But the measurements showed that none of the HO2 actually stuck. And that was inconsistent. And that challenged this work. And by the way, I remember giving a talk in Canada about this finding. And some of the experimenters decided to go back and remeasure. And they actually found that the measurements showed that 90% of the HO2, stuck. and so the measurements started to become consistent with the theoretical findings, and that was actually rather exciting. But now when you put in this new data into atmospheric models, what we were able to show is that there was missing chemistry, as the original measurements were showing that there was missing chemistry. And indeed, there is that missing chemistry with the HO2 interacting with droplet surfaces, and that you can miss out on that accountability. Well, let me just tell you, since this work, we've gone on and looked at other areas and other chemistries. We've looked at accommodations, and I'm going to give you another example to tell you an important thing. We've now looked at radical species and on these interfaces and how they react. And I'll tell you a little bit, well, I'll just sort of summarize our finding on that. I won't go into excruciating detail. But I'll tell you something really, truly exciting and unusual that we've recently discovered about water droplet surfaces that no one has actually seen and observed before, and it too is rather profound. But let me go off on this accommodation just one more time, and I'm going to go off on this. I'm looking at chlorine oxide. Now, many of you, when what do you know about chlorine and ozone? What do you know about chlorine and ozone? That chlorine destroys ozone. So what happens is that chlorine destroys ozone, give you chlorine oxide and O2, and that chlorine oxide can go back and also remove oxygen atoms and destroy ozone. Mario Molina and Sherry Rowland got Nobel Prizes in '96 for discovering that chlorine actually destroys ozone in a catalytic way. And this is the chemistry that highlighted a portion of Mario Molina's contribution involving chlorine oxide. One of the things that we did was there's an important species that's produced because of the chlorine oxide. And the chlorine oxide has an unpaired electron at the oxygen site. And when those two chlorine oxides come together, they formed an OO bond, and hence forms a chlorine dichlorine peroxide species. And that ends up in chemistry destroying ozone in another catalytic way. And that was Mario Molina's additional contribution to the Nobel Prize as well. But we argued that in the presence of clouds, that may not necessarily be the chemistry. And in fact, when we look at chlorine oxide in the presence of clouds, what we find is that the cloud surface orients the radical. It accommodates it, so i.e. it will stick, but in the sticking process, it has a selectivity of orienting. And in its orientation, all the chlorines are sticking out, and the oxygen part is embedded and protected by the water molecules of the interface. Well, what's so important and special about that? Well, what's important and special about that, what it means is that all that gas phase chemistry that said the chemistry is going to happen at the oxygens, you can toss that out the door, because it's no way that it's going to see an oxygen from the chlorine oxide. It's going to see chlorine. So now the pathway of the chemistry is altered by the selective orientation of the radicals that the interface introduces on the species. And so now what happens is, and that just kind of summarizes what I just said, the interface orients the radicals, but in that orientation, it selectively changes the course of the pathway. Instead of producing the chlorine peroxy species, it produces one of the other isomers that goes on and generates the chlorine. And that was exciting because that started to explain a lot of new data. One of the things I'll just say on on the reactivity side, and it's exciting. If you read CNE News right now, one of the exciting areas that's kind of being highlighted right now is some work coming out of Stanford and Purdue University. Out of Stanford with Dick Zare, and also Graham Cooks at Purdue. And one of the things that they've actually found is that reactions on microdroplet surfaces, what they're finding is an acceleration of reaction, almost 1,000,000 or 1,000 to 1,000,000 fold. But they're also finding that they can change the kinds of product distribution from those reactions on microdroplets. So right now, what's happening is kind of people are now exploring this. A paper that just recently came out and also been highlighted, where they're using acoustic waves to generate these little droplets, and then they send the droplets to gaseous species where they induce reactions to produce chemistry. So instead of using a lot of bulk chemistry and a lot of solution, use little micro droplets to accelerate that chemistry and to price that. But one of the things that we've actually have been working on is detailing that chemistry, and we found that it's the waters on the surface of those droplets acting as dynamical aggregates that actually accelerates a lot of that chemistry. Now, I won't talk about this here because I need to kind of be a little bit selective of and mindful of the time, but this is work that we've been working on as well. But what I want to kind of talk to you a little bit about is something that we discovered about the interfaces acting as a catalyst. And I'm going to talk about it within the context of glyoxal, which is a byproduct of oxidation of organics that come from a lot of industrial processes. And as you know, in glyoxal, there's a cis and trans configuration. But in that cis and trans configuration, one of the things that we find is in the gas phase, glyoxal prefers the trans configuration. But the interface, what we start to see is that the interface starts to catalyze that cis-trans isomerization process. And now let me see if I can work this here and show you something really kind of cool. Oh yeah, okay, so I have to go into presentation mode. And where's that? Up. Where's that? Presentation mode? Yeah, sure. There we go. Where's that presentation? Oh, right there. Okay. All right. Okay. Is it there?
Yes.
Okay. All right. No, stay right here.
Yes,
and
I'm not moving.
don't go anywhere. Okay. All right. So here's the cis form. And one of the things that we saw, if we started in a trans, and as the trans approaches that water droplet, the water kind of catalyzes it. And any trans that's not catalyzed into the cis, and if it hits that surface, the water just keep it right at the surface. But the cis that is able to catalyze, if it hits, I'm sorry, the transform starts to go on in. You can see it's trying to go on in. If we run this simulation on out to, about 50, 60 picoseconds, it goes on in. It's the cis form that really stays up at the interface. So now what we start to see is that the water droplet surface starts to select out conformations of what it goes in and what stays out at the interface. So now when I look at the cloud droplets up in the atmosphere, not only is it orienting molecules, not only is it accelerating molecules, but it's kind of selecting out things. So now if we're kind of thinking of left and right chiral systems, which are kind of essential for origin of life kinds of things, we can now start to see how clouds have maybe played some important roles in kind of pre-selecting out particular chiral structural selectivity, for that to happen. Now, one of the other things I'm going to do, all right, now how I get back? I just click on this again.
It was the other one.
Okay, all right, which one? Yeah.
Do you want to go back?
Yeah, I want to go back. And then I'll come back to that one. Yeah.
2 seconds, and you'll be back here.
Yep.
Okay, and now
oh, there it is.
mode.
Presentation mode. Don't go back. He's a good chair. He's been bailing me out all day. So one of the things that we're finding in our laboratory that cloud water droplet surfaces, are playing catalytic roles in changing reactivity of species at the interface, changing that reactivity to be much faster than what you're seeing in the gas phase, not by a factor of 10, but orders of magnitude, almost a factor of 1,000,000. Got the special accommodation, how that accommodation changes reaction pathways as well. But we're also now seeing that the interface also catalyzes reactions at the atmosphere. But we discovered something else. And remember in this talk, in the slide, I put down here that cloud droplets and aerosols can act as carriers of reactive species. Remember I told you that there are two things that cloud droplets did. Now he's standing up. I'm just going to sit down here for a little bit. All right. You remember I got to talk to you about the roles of clouds kind of deflecting off radiation and keeping that radiated balance of radiation hitting the surface. It also absorbed stuff like HCl and ultimately rained it out, and that's how it cleanses itself of the atmosphere of a lot of species. And that's how clouds also work as kind of absorbing and raining out stuff. But what happens if that stuff that's now embedded in that cloud droplet surface rely on acid-base reactions to react with it, but there's incomplete reaction even within the bulk, and now all of a sudden wind convections will start moving that stuff throughout the atmosphere, but not only just horizontal, but vertically on up. And as it moving that stuff vertically on up into lower temperatures, those cloud droplets starts to freeze. What happens to that stuff that's in the cloud droplet? Does it stay in the ice that is formed? What does it do? Now, so, we got some young, bright chemists here, and I'll just be honest, I've kind of given up of saying what it would do. So you guys are smart by not answering that question. But I tried, and I had a definite opinion. But everything I've done so far, I've actually proved I have no good chemical intuition whatsoever, because I've proved myself wrong every time, including this scenario. And right now I'm going to pick on ammonia. And, and I picked on ammonia because at the time in which we were exploring this, we're in Nebraska. A byproduct of all the agriculture, processing in Nebraska is generation of ammonia. Am I right, girl? Am I right? Okay. And, but ammonia doesn't really stick around very, very much. And one of the reasons why it doesn't stick around very much, it's very reactive towards OH radical, and it's also very easily taken up by clouds, and you now get acid-base reactions that also remove it. So the effective lifetime of ammonia is very, very short. And this is kind of back in 1986, what you kind of expected that if you go from the ground on up into the atmosphere, up into the higher up altitudes, the ammonia just really drop off because nothing really makes it up that way. But measurements back in 2016 said, hey, something's going on up here that, at high altitudes, higher than 10, where the ammonia should be really 0, we're seeing huge amounts of ammonia, showing up in there. And why? Is it coming from aircraft? Where's the source of, is there new chemistry generating that, et cetera? Well, one of the things that we kind of discovered is something kind of new and cool. So if you now take ammonia and put it into a water droplet, and if you run this actually shorter than 10 nanoseconds, you see the ammonia is kind of really distributed through here, and you can now start seeing, as you lower the temperature, on this water droplet, you can start to see the ice cages being formed, that at 70 nanoseconds the ice is formed, but the ice structures are pushing the ammonia on out and actually up at the surface. Now, Chief, if you can get me through. Yeah, master of ceremony and bailing me out of trouble here. I really appreciate this. And that's right. And now we go here. Yeah, and now is that right? Yeah. Okay, all right. Yeah, and now we click. And now here's the ammonia in that water droplet, and we're now freezing that water droplet. You can see the ice structures being formed, and you can see those ice structures really pushing the ammonia out at the top, okay? And we'll run this on out. Maybe one or two will still, okay, one's kind of getting stuck up there. And now, Chief, if you click on that one right here, and now ammonia that's now at the top, and you run that out, pop, it's on and out, okay? So now, as those water droplets carrying ammonia, and those water droplets are convected up into the stratosphere or the tropopause, and et cetera, and the temperature is driving the freezing of those droplets, that stuff will, freeze the stuff on out, and it's released up into the atmosphere. So, yep. Oh, there we go. Thank you. Thank you so much, my friend. Yep, no, we're definitely okay. And so now we're able to explain a lot of that data that was not really being able to explain before. And now we've identified how we can now explain the transport of a lot of chemical entity on up into higher regions of the atmosphere without necessarily explaining new chemical mechanism for producing it, but it's really through the transport through cloud droplet surfaces and the freezing of those droplet surfaces, releasing that stuff into the atmosphere. Where everybody, what have I learned? Water is important. And with that, everybody, I really want to say thank you.
Professor Francesco, thank you very much for your nice talk. If you have questions, we have time for a few of them. So,
fire away.
Questions, guys? Don't be shy. Students? Yes, there, one. Give the mic to.
Hello.
Yeah.
Thanks for your talk.
Yeah, thank you.
I've been reading about ideas for quality and conjugation HO using atmospheric engineering and
geoengineering.
stuff. Yeah. So I was wondering, what do you think about that? Do you think that that's going to result in chemistry that we don't know what's happening and altered atmosphere in ways we can't predict, or do you think that it's a good idea to help combat climate change?
Well, when I was a young assistant prof, and naive, in fact, one of the things that I got me curious about this is I thought we could be clever enough to design something that we can put up into the atmosphere that will really remove a lot of these things, a little bit on the geoengineering side. But one of the lessons I learned is that when you do that, you may have fixed one problem, but what you've introduced may have created another problem. Okay, and of course, when do you stop correcting the problems that you've introduced solve one problem. And, and so I kind of, after a lot of thinking I was also very clever, I felt that perhaps maybe the best thing to and the way out of this kind of predicament is to be more proactive about minimizing the stuff that you put into the atmosphere from the very beginning. And that means being a little bit more creative about recovery of stuff, recycling stuff, trapping stuff at the source rather than putting it in the atmosphere, because once you put it in the atmosphere, it's hard to recover that. And then try to geoengineering, you introduce additional problems. Now that didn't stop me from thinking about geoengineering and even playing with it, as well. And in fact, we published a paper about geoengineering Mars, and I learned some very valuable lessons around that. That's kind of made me to kind of step back and think about being more proactive at the source of things than later on. Very good question. Very good question.
Okay, more questions?
Excellent question.
Hyping, Professor Hyping. Professor Cheng.
Thank you, fascinating. So the question is, you're measuring ammonia with two methods. In the old method, you said the upper atmosphere has very little. Now, is that new methods so that you find them at higher concentration?
Actually, so some of the, so it's not a method-dependent measurement. So that's really the answer to your question. It's not a method-dependent measurement. What the dependence is the time in which you're making the measurement. So one was kind of pre-1990s. The other one's 2016, okay? And the other ones and measurements in 2000 are satellite measurements. But all the measurements pre-1990 were both from platform and satellites as well. They were all consistent about that. It's just something happened in that time frame, but there was a buildup of ammonia, at the higher atmospheres, and there was a real intense effort to really try to understand, what that was, what that was from. So they thought it was perhaps a new source, maybe just the intensity of the number of, airline flights across, the Atlantic or Pacific, but the data didn't really, from the satellites, didn't match the modeling of those kinds of scenarios. Looking at, ammonia that's been trapped or unreacted in those droplets, being pushed out, actually was the way that the best one that came close to simulating the shape and the timing, of that distribution.
So, if I may then follow up,
Mm-hmm.
so if it's due to water droplets, you then see distributions correlating to the clouds or waters?
That's correct. And I didn't really show you that data, but we see those correlations as well. And that's published in the PNAS paper. Okay.
Thank you.
Is that it?
Yeah, I think so.
Really? Sure.
So-
Okay. All right.
Yeah, so
All right.
basically now we are going to award ceremony. Professor Francisco is kind with us, and basically he will give the words. I will basically say some words, and also we'll have a guest among the words. So the first one, it's a John Paul Clay Award. It's for, this is the third edition of this award, and it's going to Chanel Hutchinson.
Yay!
Here she is.
Ta-da! Oh,
Yeah.
congratulations. All right. Is someone take a photo?
Photo,
Photo?
photo, no,
Photo?
photo, please.
All right, get
Okay,
the
come,
cell
come.
phones. Photo.
2, 3.
Awesome,
Okay.
awesome.
Congratulations.
Congratulations,
So,
congratulations.
Chanel is doing research with Professor Malik Karachi. She's, we can say that she's very consistent, very thorough, and she's a self-made and very ambitious student. Congratulations again. Okay. Years ago, we make a new award called Student Citizen, which celebrates somebody which is volunteering. So we celebrate somebody which is volunteering his time. You can see he volunteered his time. It's Wildy. Wildy Joseph. Basically, everybody asks everybody about him. Everybody says he's likable. He is a guy which is devoting his time, helping the other, doing tutoring, and helping, and doing research with Professor Lopez. Congratulations.
All right, my boy. Congratulations, man.
And get well.
Yeah.
Next time you have to dance.
Yeah. Come on.
Yeah.
Yeah. There we go.
Okay.
Awesome.
Okay. For next award, I would like to invite the Dean Mills to come up and to talk about. Dean Mills? Yes, I want to advance. Andre, you are here?
All right, Andre.
Not me, the other Andre. Yes, 1 sec.
All right, Andre. You got to stand up. All right, big thanks.
Does this work?
He's going to talk about it.
Let me talk about Barry for a minute. So before we honor Andre, I want to talk about the naming of this award. So this is the Barrington Downey Award for excellent teaching by an adjunct instructor in our department. Barrington Downey is someone who grew up in the Bronx, went to Bronx Community College when he graduated from high school, and then he appeared in my lab at Hunter College in the early 90s. Right out of BCC, wanted to do some research, and worked with me. He then graduated from Hunter in the 90s, went to industry, came back. I lost touch with him. I gained touch with him. We got back together. And then in around 2014, he came back to Hunter, worked on a master's degree. We hired him as an adjunct. He's a phenomenal teacher. And then I came to Lehman. When I came to Lehman, he said, hey, I'm coming to Lehman too. So he was teaching in the spring semester in 2016 at Hunter. I was going to hire him in the fall of 2016. He passed away. He was 48 years old. He was extraordinarily loved by his students. When we went to his funeral, his entire class came because it was in the middle of the semester. So this was a very difficult time. We thought, how can we honor his memory? And the Sweeny Lecture is the perfect place to honor his memory. Now, the internet preserves everything, so rate my professor. It's very strange. But let me read to you what's on Rate My Professor for Barrington. So I think this exemplifies Professor Sweeny. It exemplifies what we've tried to do. It said about Barry, he's teaching a general chemistry lab. He's an intelligent instructor who will force you to think. And students don't always like that. He will force you to think your way through questions. But he does that, but he'll still do his best to provide you everything you need to succeed. And I think that's really the way I want to think about Barry. I think he fits right here within the Sweeny Award. And so I am honored and excited, because I get to do this, I think, to present the winner of the Barrington Downey Sweeny Award, which is Andre Ferguson. And wait. No, I got to say something about Andre. Can't help myself, right? So Andre graduated, I think, 2 years ago from Lehman. He worked his way through, like many of you, but he was, if you happen to know him, he's a public safety officer here at Lehman. Every now and again, he'd come by in his uniform. Was majoring in biology and chemistry, right? Biology? Psychology. Oh, okay. So, and thinking about being pre-med and coming back, he was in our general chemistry class. I had him. I have to say a couple things about Andre. He's amazing. He never, ever got 100 on a test because he always missed the easiest question. Go figure, we don't understand this. I would look at and say that almost every student in class got the question right. I could count on Andre getting it wrong. But if it was a question that most students got wrong, I could count on Andre getting it right. so when he finished the chemistry, of course I had to ask him to teach for us, because that's a perfect student, right? He was my TA. He was amazing as a TA. He could do both, explain the content, help the students, and then when they weren't quite focusing, he could get them to focus. Security guard, it's good for teaching.
Of course.
Good,
of course.
Anyway, I wanted to say congratulations to Andre. I'm glad you're the Barrington Downey winner.
Okay.
Gotta go also over here.
Okay. So, okay, everybody.
There we go. There we go.
Everybody.
Okay.
Pictures. Done? Okay.
Okay.
Thank you very
Awesome.
much.
Awesome, Andre.
Okay.
Congratulations.
Now,
man.
I want to go back a little bit to welding. Besides doing the day job, helping students and doing everything, he's a mechanic. During the night, he's doing mechanic. And also, this connects with my last award. So, the last award is Sweeny Lecture Award, which is given to Edrosian. Basically, I learned that his name is French, and I try to pronounce correct in French, Edrosian. Edris had an interesting pathway. He started in a different way. He go to Bronx Community College, correct? And then he went to be mechanical, yes? So, and he decided, nah, I don't like too much. Let's go back to school. Come to Lehman, and he scored excellent in every single class. He, in fact, has the highest GPA all over both BA and BS, 395. Yeah?
Wow.
Okay,
Wow.
so he's already accepted at Kansas State as in a PhD program, and we wish him good luck. So this award
Yes, all right, my boy. Congrats. Okay, there we go. There we go. All right, there we go. Awesome. Awesome. Merci. Merci beaucoup.
Okay, so this concludes. Thank you very much.
You're welcome. I can sit down now?
Yes, we can sit down. Yes. If you want to see her, it's okay. So this kind of conclude our lecture. However, I have only one thing to add. So if you have time and money, please don't forget to donate to Lehman College. We create awards. Unfortunately, today, we couldn't give the awards the money checks. Basically, those awards contain a monetary a check, which should come. So sooner or later, the students will receive a check. So that is not our fault. Yes, our new rule is in place, and it basically should be written once per month, and I don't want to get there. But if you have money and interest, please help our students to get more awards and to continue this. And of course, based on our program, now it's the most important part, dinner. Everybody is invited in 3:30 who make a reservation. It's invited there, and let's have a good night and meet with you next year, and hopefully we'll have another nice 40-year anniversary of the Sweeny lecture. Thank you very much.